Hello everyone, welcome to quick revision series of strength of materials. In this video, we will be discussing about material properties and stress strain curves. In brief, I will be explaining the material properties and I will be explaining the stress strain curve of mild steel, and at last I will be explaining the types of stress strain curves. Now let's see what are the material properties. First we will be seeing about strength and hardness. Next we will be discussing about elasticity and plasticity. Next we will be discussing about malleability and ductility. Next we will be discussing about stiffness and flexibility. Next I will discuss about creep, fatigue. Next I will discuss about resilience and toughness. Now let's see about strength and hardness. Strength and hardness look similar, but technically these two terms are different. Strength is nothing but ability of material to withstand load without failure. This strength is an internal property of a material. See, if we take a metal and if we apply load, the maximum load which can be applied on this without failure is known as strength of this metal. Whereas hardness is the surface property of the material, which has ability to resist abrasion. See, if we take a metal and a cardboard box, we can easily remove the particles from the cardboard box, whereas it is very difficult to remove the particles of the metal. That means metal is more hard than the cardboard box. A material is said to be hard if it is difficult to scratch, wear, penetrate. If it is difficult to scratch, wear and penetrate, that particular metal is supposed to be called as hard material. Now let's talk about elasticity and plasticity. What is elastic property of a material? See, if we take a particular bar and if we apply tensile load, there will be a certain deformation in this. If we remove this load, if this particular bar regains its original shape, then it is known as elastic material. Graphically, this is stress strain curve of, if this is the stress strain curve of the bar, this is the loading part. If we remove the load, if in unloading case also, if this follow the same path, then this metal is known as elastic material. Whereas in case of plastic material, after removal of load, the body doesn't regain its original shape. This particular deformation is known as plastic deformation. This is a permanent deformation which cannot be regained again. In this case, the stress strain curve doesn't follow the original path. It may be something like this. This particular deformation is known as plastic deformation. Now, let's see what is malleability, ductility, creep and fatigue. Malleability, the property of material by which it can be drawn into thin sheets. The perfect example of malleable material is aluminium. We know aluminium foils, they are very big and thin. So, aluminium is perfect example of malleable material. Next, we will see what is ductility, the ability of material to be drawn into thin wires. In this case, we will be applying tensile load and the material will be elongating without fracture. This property is known as ductility. Example of this ductile material is gold. Next, we will be seeing what is creep. Creep is nothing but a permanent deformation due to constant load under elastic limit after a long passage of time. That particular deformation will be a permanent deformation, and that will be due to constant load or dead load. This depends on time. The creep particularly depends on load, time and temperature. More the temperature, more will be the creep. That means at higher temperature, the creep will be more. At higher temperature, we have to consider a creep also. Now let's see what is fatigue. Fatigue is nothing but progressive or localized structural damage that occurs due to cyclic loading. Example, let's take an iron scale. Hold it with two hands and move it up and down continuously till it breaks. See, if we observe, it breaks at center when we hold it with two hands and move it up and down. That means because of cyclic loading, that is moving up and down, it breaks in between. That particular failure is known as fatigue failure. Now let's see what is stiffness and what is flexibility. Stiffness. Stiffness is nothing but resistance of a material against deformation. The more, if we take two materials, let's take this steel and this is of aluminium. If we apply load, there will be a little deformation, and here in this case there will be more deformation. That means steel is more stiffer than aluminium. See, mathematically stiffness is defined by load per unit deformation. The more the deformation, less will be the stiffness. That means if a stiff material will have less deformation, and the material which is not stiff will have more deformation when the load is applied on it. Now let's see flexibility. Flexibility is exactly opposite to stiffness, which is nothing but deformation per unit load. That means generally we'll be saying this metal is more flexible. That means easily deformable or something like that. So the more is the flexibility, more will be the deformation. Here aluminium is more flexible than steel. Now let's see what is resilience, what is proof resilience and what is modulus of resilience. Resilience is nothing but strain energy that can be stored in a given volume of material under elastic limit. Now, strain energy is nothing but we can directly consider area between load and deflection curve. Now, in case of resilience, we will be considering at any point between O and A, whereas in case of proof resilience, we will be taking load deflection curve only, but we will be considering up to proportionality limit, whereas in case of modulus of resilience, it is strain energy stored per unit volume, which means we have to consider a stress strain curve and up to proportionality limit. We can also consider load deflection curve, but after calculating strain energy, we have to divide it per unit volume. Okay. Modulus of, this is the difference. In this case, we will be considering at any point before elastic limit. In this case, we will be considering up to elastic limit or up to proportionality limit. In this case, we will be considering up to proportionality limit, but this curve is a stress strain curve. Now, we know up to proportionality limit, it is a triangular variation, that linear variation. So, directly we can consider it as a triangle and we can find area half into P into delta. Whereas proof resilience, this load will be elastic load and this deformation will be last proportional up to proportionality limit, deformation at proportionality limit. Whereas in case of modulus of elasticity resilience, we will be considering half into stress into strain. If we write strain as stress by Young's modulus, we will be getting modulus of resilience as sigma y square by 2e. Now let's see what is toughness and what is modulus of toughness. Toughness is nothing but the resistance against impact loading. It is the maximum strain energy that can be stored in a given volume up to fracture point. Remember this. In case of resilience, we will be considering up to proportionality limit, whereas in case of toughness, we will be considering up to fracture point. Now, in case of modulus of toughness, similar to modulus of resilience, we will be considering a stress strain curve, and area we will be considering up to fracture point. Normally, if we consider brittle materials are more resilient, whereas ductile materials are more tough. Generally, resilience depends on yield stress, whereas toughness depends on fracture stress. So, I have discussed some material properties. Now, let's come to stress strain curve of mild steel. Mild steel is a metal which has high ductility. In case of mild steel, the yield stress in compression and yield stress in tension are almost same, which is 262 and 250, and the coefficient of thermal expansion is 12 into 10 power minus 6. The Young's modulus in tension and compression is equals to 2 into 10 power 5 MPa. And these are some values which need not be remembered, but just know this. Just know that the yield stress in compression and tension are almost equal, or the Young's modulus in tension and compression is equal, which is equals to 2 into 10 power 5. Now, let's come to stress strain curve. In this, these points are important. Now, let's see each point one after the other. If we take A is nothing but proportionality limit. Like OA is from A to O, this is linear portion of stress strain curve. In this region OA, Hooke's law is valid. And this point B is known as elastic point. Till B, if we apply any load and remove load, this path will be followed again, like loading path and unloading path will be same till point A. C dash is known as upper yield point. C is known as lower yield point. C dash is known as upper yield point, C is known as lower yield point. The portion CD is known as yield plateau. In this portion, the metal will be plastically deforming. That means without increase in stress, there is a continuous deformation. This region DE is known as strain hardening region. In this case, the metal gains its strength, and its strength increases continuously up to a certain point, which is known as ultimate strength point. After E to F is known as strain softening region or necking region. In this case, the cross section of the metal decreases drastically. and it will tend to fracture. At point E, it gets fracture this way. At point F, this get fracture this way. See, actually, in this the cross section of metal is decreasing. That means we know that stress is load by area. Area is decreasing, so stress have to increase. Actual stress strain path looks like this, but we generally use this one, engineering stress strain path. Actual one looks like this. This is stress strain curve in brief. These are some points which are to be remembered. Now let's see what is proof stress. This proof stress concept is not applied for brittle materials because in case of brittle materials we consider ultimate strength, whereas in ductile materials we will be considering yield stress. So in some ductile materials we will not be getting some perfect yield point. In that case, in order to find the yield point, we will be approximately considering proof stress as a yield stress. Now let's see how to calculate it. After drawing a stress strain curve, a normal stress strain curve normally, we have to consider a strain with 0.2%, that is 0.002, and we have to draw a line parallel to stress strain curve this way. It will be intersecting the stress strain curve at one point. That point is nothing but proof stress. This is generally used for ductile materials which doesn't have a proper yield point, like example aluminium, copper, silver, gold, etc. Now let's see how carbon content affects the brittleness and ductility. If we see the graph, the steel with higher carbon content is more brittle than the steel with medium carbon content and low carbon content. Whereas if we see ductility property, the steel with lower carbon content has more ductile property, whereas higher carbon steel has 0 or less ductile property. That means carbon content increases, ductile nature decreases. And if we observe the fracture point, see, in case of higher carbon steel, the fracture point is at very less strain, whereas in case of medium carbon steel it is here, and whereas in lower carbon steel it's here. That means as the carbon content increases, the fracture point will be at lower strain. Now let's see different types of stress strain curves. These curves are frequently asked in exams. First one is linear elastic stress strain curve. In this case, the stress strain curve is varying linearly and it is elastic. That means loading and unloading will be of same path. This is non-linear elastic stress strain curve. And this is elastoplastic stress strain curve. That is, up to certain region it is elastic and after that it is of plastic nature. And this is perfectly plastic stress strain curve. See, from start itself it is of plastic nature. This is linearly elastic with strain hardening region. Up to certain region it is linearly elastic and after that it is a strain hardening curve. If they ask linear elastic with strain softening, the stress strain curve looks like this. And this is a perfectly rigid stress strain curve. Okay, with this I will be ending this video. If you find this video useful, you can share it with your friends. Thanks for watching.